Hello friends, myself Anjali Shinde, Associate Professor, Department of Mathematics, S.V.K.T. College, Diwali Camp, Nasik. In the previous lecture, we have studied the separation of variables and variation of parameters method. Today, we are going to see what is exact differential equations. Given a differential equation, y dash is equal to f of xy, that is dy by dx is equal to f of xy. We can rewrite this equation as m dx plus n dy equal to 0. Generally, the differential equation, when we are going to study exact differential equation, we will firstly rewrite that equation in this form, m dx plus n dy equal to 0. Now, when an equation is known as exact differential equation, the definition is given as a differential equation that can be obtained from its primitive that is solution by differentiating the solution without any further elimination or reduction is known as exact differential equation. Now, what is the meaning of this? For example, consider a solution x square y equal to c. If you differentiate this with respect to x, we get 2xy plus x square dy by dx equal to 0. Equation 2 is obtained from equation 1 by direct differentiating this with respect to x. So, observe that this equation, we rewrite it as 2xy dx plus x square dy equal to 0. So, this equation is exact differential equation. It is exact because it is obtained by differentiating its solution directly and without any elimination. Observe, x square can be taken common. If you take x common, we will get the equation 2y dx plus x dy equal to 0. But we are not cancelling x because we want it to be exact. We keep it as it is. Don't do any elimination or reduction. So, we are not considering, we don't cancel x from this. We say that this is exact differential equation. Why it is exact? Observe that this equation 2xy dx plus x square dy can be written as derivative of x square y. Observe that it is derivative of x square y. What is it? It is nothing but 2xy dx plus x square dy equal to 0. So, any differential equation, when we say that it is exact differential equation, m dx plus n dy equal to 0 is said to be exact differential equation if there exists a function uxy having continuous second order partial derivatives such that m dx plus n dy is equal to du. See, this is exact because it can be written as 2xy dx plus x square dy is equal to d of x square y. So, this becomes exact. So, the simple definition of exact is m dx plus n dy equal to 0 is said to be exact if there exists a function u of xy having continuous second order partial derivatives such that m dx plus n dy equal to du. For example, suppose we have the equation x dy plus y dx equal to 0. Then this equation is exact differential equation. Why we say that this is exact differential equation? The reason is that this equation can be written as x dy plus y dx is nothing but derivative of xy, d of xy. So, u is nothing but xy. That is, u is equal to c or xy is equal to c is its solution of this differential equation. Xy equal to c is the solution of this differential equation. If you differentiate this solution, xy is equal to c, we will get this differential equation. So, this differential equation is known as exact differential equation. There are many examples of exact differential equation. We are going to see what is the condition, because it is not every time easy to find the function u of whose derivative is given on this side, and therefore we are going to see what is the necessary and sufficient condition for the equation m dx plus n dy equal to 0 to be exact. So, consider the next theorem. It gives the necessary and sufficient condition for differential equation to be exact. The theorem says that a differential equation or a necessary and sufficient condition for the differential equation m dx plus n dy equal to 0 to be exact is dabba m by dabba y is equal to dabba n by dabba x, or in another notation, if my partial derivative of m with respect to y is nothing but equal to partial derivative of n with respect to x. So, this is the condition in another notation. We will prove this theorem. Firstly, prove that the condition is necessary. So, it is given that the equation m dx plus n dy equal to 0 is exact, and we want to prove that the condition is satisfied, that is dabba m by dabba y must be equal to dabba n by dabba x. Now, see by definition, the equation is given to be exact. So when we say that the equation is exact, if there exists a function u such that m dx plus n dy is equal to du. So by definition of exact, there exists a function u such that m dx plus n dy is equal to du. From calculus, we know that du, that is total derivative, is nothing but dou by u by dou by x dx plus dou by u by dou by y dy. So from calculus we know this, that total derivative is always equal to this step. Now on both sides compare the coefficients of dx and compare the coefficients of dy. So comparing the coefficient, we get m is equal to dou by u by dou by x and n is equal to dou by u by dou by y. Differentiate this with respect to y. So what is dou by m by dou by y? It is nothing but dou by y of dou by u by dou by x. That is nothing but dou by 2u by dou by y dou by x. Similarly, differentiate n with respect to x. What is dou by n by dou by x? It is dou by x of dou by u by dou by y. So it is nothing but dou by 2u by dou by x dou by y. Observe that dou by 2u by dou by y dou by x is always equal to dou by 2u by dou by x dou by y, as it is given to be continuous, and therefore as we know that mixed partial derivatives dou by 2u by dou by y dou by x, it is same as dou by 2u by dou by x dou by y. Due to continuous function, we have dou by m by dou by y is same as dou by n by dou by x. So the differential equation m dx plus n dy equal to 0. If it is exact, then dou by m by dou by y is always equal to dou by n by dou by x. This is necessary part. Now consider the sufficient part. The condition is sufficient means it is given that, so the second part, that is converse part, it is given that dou by m by dou by y is equal to dou by n by dou by x. This is given to us, and we want to prove that the equation m dx plus n dy equal to 0 is exact. This we want to prove. To prove this, we will start with assumption integral m dx is equal to v. We are considering a new function v such that v is equal to integral m dx. Now partially differentiate this with respect to x, treat y to be constant. So we get dou by v by dou by x is equal to m. Note that because we are treating y to be constant, we can write v as integral m dx over y constant. We are partially differentiating this with respect to x, but we treat y to be constant and we get this step. So we have m is equal to dou by v by dou by x. Now differentiating this with respect to y partially, we get as m is equal to dou by v by dou by x. This implies dabba m by dabba y is equal to dabba y of dabba v by dabba x. This is nothing but dabba 2v by dabba y dabba x. But we know that mixed partial derivatives are equal. Therefore, this is nothing but dabba 2v by dabba x dabba y. As dabba 2v by dabba y dabba x, it is same as dabba 2v by dabba x dabba y. Also, from given condition 1, dabba m by dabba y, it is equal to dabba n by dabba x. So, use 1, this dabba m by dabba y, it is nothing but dabba n by dabba x by 1. That is given condition, that dabba m by dabba y is same as dabba n by dabba x, and therefore we get dabba n by dabba x is equal to dabba 2v by dabba x dabba y. Or we can write this as dabba n by dabba x minus dabba 2v by dabba x dabba y equal to 0. That is dabba x of n minus dabba v by dabba y equal to 0. Integrate this with respect to x, treating y constant. We get n minus dabba v by dabba y is constant. This is constant of integration. Now observe that we are treating y to be constant, and therefore I take this constant of integration. Suppose it is equal to phi dash of y. As y is constant, and therefore this is assumed to be constant of integration. So we have n minus dabba v by dabba y is equal to phi dash y, or n becomes dabba v by dabba y plus phi dash. We have the value of n, we have also the value of m. So put these values of m and n in LHS of second. So if you consider m dx plus n dy, we get the values equal to m is nothing but dabba v by dabba x dx, m value is dabba v by dabba x dx as it is, plus n value is nothing but dabba v by dabba y plus phi dash y dy. This simplification becomes dabba v by dabba x dx plus dabba v by dabba y dy plus phi dash y dy. Observe this part. From calculus we know that dabba v by dabba x dx plus dabba v by dabba y dy is nothing but total derivative. So this is nothing but dv, because we know that dv is nothing but dabba v by dabba x dx plus dabba v by dabba y dy. Therefore this part becomes dv plus phi dash y dy is nothing but written as derivative of phi y. Derivative of phi y is phi dash y dy. So this total can be written as d of v plus phi y. Observe that m dx plus n dy can be written as d of v plus phi y. This is our u. We know that a differential equation is exact if it can be written as m dx plus n dy is equal to du, where u is a function of x and y. So let us assume this to be u. So we are able to write this as m dx plus n dy is equal to du, where u is nothing but v plus phi y and u is equal to c is the solution of this differential equation. We have proved that the equation m dx plus n dy equal to 0. This equation can be written as m dx plus n dy is equal to du, and therefore it becomes exact differential equation. So if we know that dA by m by dA by y is same as dA by n by dA by x, we are able to show that the equation is exact. So this proves the sufficiency of the condition. So what we have seen here, that a differential equation m dx plus n dy equal to 0 is exact if and only if dA by m by dA by y is equal to dA by n by dA by x. That is necessary and sufficient condition. Now we want to find the rule, working rule that is used to solve any exact differential equation. So we will consider the same equation. See, what we have seen here is the equation m dx plus n dy is equal to du, where what is u? U is the solution. U of xy is equal to c is always the solution of this equation. What is this u? It is nothing but v plus phi y. U is nothing but v plus phi y is equal to c. Now see what is v. Here we have written in the first step, we know that from this step first, we know that v is nothing but integral m dx over y constant. That is our v. And plus, what is phi y? It is nothing but integration of phi dash y dy. Phi y is nothing but integration of phi dash y dy. So v is nothing but integral m dx over y constant, and phi y is nothing but integration of phi dash y dy. Now see what is this phi dash y. From this step you will observe that what is phi dash y? Phi dash y is nothing but all the terms in n which are only functions of y. Phi dash y are nothing but all the terms in n which are only functions of y, and therefore we can write down this as m dx over y constant plus integral terms in n free from x dy is equal to c. Why we get this? Because from this definition we observe that phi dash y are nothing but terms in n which are only functions of y, that is those are free from x. So we consider integral m dx over y constant plus integral terms in n independent of x or free from x dy is equal to c. This is nothing but solution of the exact differential equation. So this is working rule to find the solution of exact differential equation. For example, consider a simple example. We have seen that the equation x dy plus y dx equal to 0 is exact. Why we say that this is exact? Because it can be written as d of xy. X dy plus y dx. Exact means m dx plus n dy equal to 0 is exact if it can be written as m dx plus n dy is equal to du. Here u is nothing but xy. So this is exact because this can be. And this is nothing but solution. So what is the solution of this equation 1? This equation 1 has the solution u equal to c. U is nothing but xy. So xy is equal to c is the solution of equation 1 that we know. If you differentiate xy is equal to c, you will get this differential equation directly, and therefore it is exact. Now we will find this by this rule. What is our solution by this rule? The rule says that the solution is integral m dx over y constant plus integral terms in n free from x dy is equal to c. This is the solution. So integral, what is m dx? M is nothing but y here, m dx. So m is nothing but y. So integral y dx over y constant plus integral terms in n free from x. N is nothing but x here, n dy. N is nothing but x. Because there is no term which is free from x, there is no term here. So we get is equal to c. Y is constant, so y integral dx is equal to c, that is xy is equal to c. This is the solution from this rule. So we are able to find the solution of exact differential equation. We have written this as d of xy and then we say by definition it is exact. What is our condition? That can be satisfied also. See, we know that m dx, we know that the equation m dx plus n dy equal to 0 is exact if and only if dabba m by dabba y is same as dabba n by dabba x. Observe here, what is m? M is y, m dx. So here m is y. And what is n here? N dy. N is nothing but x. Find dabba m by dabba y. It is 1. And find dabba n by dabba x. This is also 1. Observe that dabba m by dabba y, it is equal to dabba n by dabba x. That is dabba m by dabba y equal to dabba n by dabba x implies that this equation is exact. So it may happen that you are not able to find this u of whose derivative is here. But you can check this condition, and checking this condition you directly get that this condition is satisfied and therefore the given equation is exact. And if it is exact, we get the solution by this rule. Consider one more example to get the idea. Solve the differential equation x square minus 2xy minus y square dx minus x plus y square dy equal to 0. We will check whether the equation is exact, and if it is exact, we will find the solution from rule. So to check this is exact or not, we will always compare the given equation with m dx plus n dy equal to 0. So compare this equation with m dx plus n dy equal to 0. So m is nothing but x square minus 2xy minus y square, and n is nothing but minus of x plus y bracket square. Find dabba m by dabba y and dabba n by dabba x. What is dabba m by dabba y? We are differentiating with respect to y. So it is nothing but minus 2x minus 2y. Similarly, find dabba n by dabba x. It is minus 2 times x plus y. You can take minus 2 common, and here it is also minus 2 times x plus y. Observe that both values are equal. That is, dabba m by dabba y is equal to dabba n by dabba x implies that the given differential equation is exact differential equation. If it is exact differential equation, what is its solution? The solution is given by the formula integral m dx over y constant plus integral terms in n free from x dy is equal to c. So integral m dx, m is x square minus 2xy minus y square dx plus terms in n. Now see what is n. N is minus x plus y bracket square. If you simplify this, see what is n then. If you simplify n is nothing but minus x plus y bracket square, that is minus x square minus 2xy minus y square. This is n. We want the terms which are free from x. So we don't want these two terms because they contain x. Only the term free from x is minus y square. So plus integral minus y square dy is equal to c. Here we are keeping y to be constant and integrate. So we get x cube by 3 minus 2y x square by 2 minus y square x minus y cube by 3 is equal to c. Or rewriting, we get x cube by 3 minus x square y minus xy square minus y cube by 3 is equal to c. So this is general solution of the given differential equation which is exact. So what we have studied today, that a equation m dx plus n dy equal to 0 is said to be exact differential equation if there exists a function u having continuous second order partial derivative such that m dx plus n dy is equal to du, or you can say that it is exact if it can be obtained from its solution by direct differentiation of the solution. In short, what is the necessary and sufficient condition? The necessary and sufficient condition for a differential equation m dx plus n dy equal to 0 to be exact is dabba m by dabba y is equal to dabba n by dabba x. And if the equation is exact, its solution can be given by the formula integral m dx over y constant plus integral terms in n free from x dy equal to c. So this is the solution of the exact differential equation. Thank you.